So hello everyone, this is Swati and this is the TikTok topic, and we are here for the aircraft propulsion and the turbo machinery course. Today we have a topic called study of turboshaft engine course noise. First we had a turboshaft engine as you can see in the diagram, and it has the introduction to turboshaft engine core noise. Turboshaft engines are widely used in aerospace applications, particularly in helicopters and some fixed-wing aircraft, where the design optimizes power generation for propulsion. However, these engines also produce a significant amount of noise, particularly from the engine core. This noise is primarily generated by the combustion process, the rotation of turbines, and the high-speed airflow through the engine. Understanding an turboshaft engine's core noise is essential for improving passenger comfort, reducing environmental impact, and complying with noise regulations. Advanced noise reduction technology and noise modeling are crucial addressing these challenges. Source of turboshaft engine core noise. The primary source of turboshaft engine core noise includes mechanical and aerodynamic components. Aerodynamic noise arises from high-speed flow of exhaust gases and air passing through the engine, which interact with various engine components. Mechanical noise is generated by rotating parts such as turbines, compressor, and shafts, which induce vibration that propagate through the engine structure and surrounding area. Combustion noise also contributes significantly as the rapid expansion and mixing of gases inside the combustion chamber creates pressure fluctuations. Analyzing this source and their infrastructure interaction helps in developing effective noise reduction strategies of turboshaft engines. As we can see in the diagram, there is a fully mixed zone where the combustion chamber is having aerodynamic noise generator mechanism. Aerodynamic noise in turboshaft engines is primarily caused by turboshaft flow and shock waves that develops in the engine core. The high pressure and high speed exhaust gases produced by the combustion process passes through nozzle and turbines, generating vortex shearing, jet noise, and turbulence. This turbulent flow induces pressure fluctuations which propagate as sound waves. This interaction between the airflow and engine components such as blades and vanes also contributes to the generation of noise. By understanding the aerodynamic of these processes, engines can develop method to the noise production by the engine core. Mechanical noise and vibration source. Mechanical noise in turboshaft engines is primarily caused by the rotation of components such as turbines, compressors, and shafts. The interaction between the rotating parts and the surrounding air creates vibrations, which can amplify by resonant frequencies of the engine structure. This vibration propagates through the engine and can be redated as sound. Mechanical noise is influenced by factors such as speed of rotation, the geometry of components, and the mechanical tolerance of the engine. A key aspect of noise reduction involves minimizing these vibrations and controlling of the source mechanical noise within engines. Next, the combustion noise and pressure fluctuations. Combustion noise is a significant contributor to turboshaft engine core noise. The combustion process generates pressure fluctuations within the combustion chamber, which are transmitted as sound waves through the engine. These pressure variations are caused by the rapid expansion and mixing of hot gases as well as the instability of the combustion process. Combustion instability in particular can lead to low frequency noise and vibrations that are more difficult to control. By improving combustion efficiency and stability, engineers can reduce the amplitude of pressure fluctuation and constantly the combustion noise produced by the engine core. flow dynamic and engine core noise. The flow dynamic inside the engine core are critical to understand the noise generation mechanism in turboshaft engines. High-speed flow through turbines, compressors, and exhaust systems create complex interactions between fluid and engine components. This interaction generates sound waves that propagate as noise. The swirling flow pattern created by the turbines, for example, contribute to vortex shading and turbulence, which in turn generate aerodynamic noise. By analyzing this flow dynamic, engineers can identify specific region within the engine where noise is generated and develop strategies to reduce it, such as optimizing component design or controlling flow characteristics. Noise prediction and modeling techniques. Predicting and modeling turboshaft engine core noise is a complex task that requires advanced computation tools and methods. Numerical simulation techniques such as computational and fluid dynamics (CFD) are commonly used to analyze the flow pattern within the engine and their impact on noise generation. Models are also employed to simulate how sound waves propagate through the engine and into surrounding environment. By combining CFD and other model, engineers can accurately predict noise level at different points within the engine, enabling them to target specific noise source and design noise reduction solutions more efficiently. Experimental method of noise measurements. Experimental methods are crucial for validating noise prediction models and understanding the real-world noise levels produced by turboshaft engines. This method typically involves placing microphones and sensors near the engine core to measure sound pressure levels at various frequencies. Techniques such as beamforming and array measurements are often used to identify the spatial distribution of noise sources within the engine. By conducting these experiments under various operating conditions, engineers can gather data on the contributions of different noise sources and refine their noise reduction strategies accordingly. These measurements are essential for assessing the effectiveness of noise techniques. As we can see in the diagram, there is a motor and the gearbox, the spark combustion chamber, exhaust turbine, power turbine, compressor stage, air inlet, in output shaft and rotor. Turboshaft engine core noise reduction strategies. Several noise reduction strategies can be employed to minimize the noise produced by turboshaft engine cores. One approach involves modifying the design of engine components to reduce the generation of noise at its source. For example, optimizing the geometry of turbine blades and exhaust nozzles can help reduce turbulent flow and vortex shading. Another strategy is to improve the engine by adding sound absorbing materials or accurate linear to the engine casing. Additionally, advanced noise controlling techniques such as active noise cancellation can be applied to counteract the sound waves generated by the engine core, further reducing noise level. Acoustic linear and noise absorption material. Acoustic linear are one of the most common noise reduction techniques used in turboshaft engines. These linears are made from the material that absorb sound waves reduction, the transmission of noise from the engine core to the surrounding environment. These linears are typically placed in the area where noise levels are highest, such as around the engine casing and exhaust ducts. The material used in this linear are designed to absorb the specific frequency ranges of sound depending on the noise characteristics of the engine by corresponding linear into the engine design. Engineers can significantly reduce the overall noise footpath of the engine. as you can see in the diagram: bearing, generator, coupling, exterior bearing. This condition is known as the noise absorbing materials. So, active noise control in turboshaft engine. Active noise control, ANC, is an advanced noise reduction technology that has been applied to turboshaft engines in recent years. ANC system use microphones and speakers to detect and cancel out sound waves generated by the engine core. The system creates an anti-noise signal that is phase shifted by 180 degrees, effectively cancelling out the original noise. This technology is particularly effective at reducing low-frequency noise such as the generator by combustion instability and mechanical vibration by integrating ANC, like a active noise control, into the engine design. Engineers can further reduce noise levels and improve the comfort and safety of aircraft. So next, moving to the design optimization of noise minimization. Design optimization is a key strategy of reducing noise in turboshaft engines. Engineers can advance simulation tools and experimental data to optimize the geometry and material of engine components such as the turbines, compressor, and exhaust nozzle with a focus on minimizing noise generation. For example, turbine blade designs can be modified to reduce vortex shading to improve flow characteristics, while exhaust nozzle can be optimized to reduce jet noise. Additionally, lightweight and noise damping materials can be incorporated into engine structures to reduce vibrations and sounds. Transmission: by optimizing the design of noise reduction, engineers can improve the overall performance and turboshaft engines. As you can see in the diagram, how the turboshaft engine is working. So, moving to next one: noise shading and engine enclosures. Noise shading and engine enclosures are commonly used in aerospace application to reduce the transmission of engine core. Noise to the surrounding environment enclosures are designed to contain and absorb sound waves produced by the engines, preventing them from escaping into the cabin. Or external environment materials such as soundproofing foam, composites, and metal barriers are used to construct this enclosure. In addition, to reduction, overall noise level shading can also help to improve the comfort of passenger and crew. Proper design of engine enclosures is essential to ensure effective noise integration without compressing engine performance or efficiency. So, impact of engine core noise on helicopter operation. In helicopter, engine core noise has a significant impact of both operational efficiency and environmental consideration. Helicopter engines, particularly those with turboshaft core, generate strident noise that can affect mission success, passenger comfort, and noise pollution. Noise from the engine can interfere with communication between the pilot and the crew, making operations more challenging. Furthermore, helicopter noise in urban areas can contribute to noise pollution, leading to the restrictions on flight paths and operations. Understanding the source and mitigation strategies for engine core noise is essential to improve helicopter design and meet regularity noise limits. Impact of turbo engines noise on performance. While noise reduction is a key goal, it is important to balance noise mitigation with the overall engineering performance. Noise control measures should not significantly compromise the engine's efficiency, power output, and reliability. For example, adding excessive weight to the engine structures in the form of soundproofing materials could impact fuel efficiency and performance. Similarly, noise reduction technologies like active noise control must be carefully integrated into the system to avoid interfaces with critical engine functions. A holistic approach to noise reduction ensures that performance is optimized while still achieving significant noise reduction. Noise regulation and certification. Noise regulation plays a crucial role in the design and development of turboshaft engines. Many countries have established noise certification standards that limit amount of noise aircraft can generate during various stages of flight, including landing, takeoffing, in-flight operations. These regulations are particularly significant and civil helicopters and aircraft operations in urban areas. To complete with these regulations, engineers must ensure that turboshaft engines meet specific noise limits, both the engine's core noise and overall aircraft noise. Clarification testing involves measuring noise from standardized conditions to verify complex and regularity requirements. Future direction in turboshaft engine noise research. Future research in turboshaft engines core noise is focused on developing more efficient noise reduction technologies and improving the understanding of noise generation mechanisms. Advancements in material science, such as the development of new lightweight noise-absorbing components, will continue to play the key role in reducing engine noise. Additionally, ongoing improvement in computational methods and simulation tools will enable more accurate predictions of noise generators, and this effect of from different design modifications, active noise control, and other advanced technologies will continue to evolve, further enhancing the ability to mitigate noise in turboshaft engines to improve the overall aviation experiences. So at last, the conclusion. For conclusion, turboshaft engines are noise remains critical challenges in aerospace engineering, particularly for helicopters and other aircraft that rely on turboshaft engines for propulsion. Understanding the source of noise, including aerodynamics, mechanical, and combustion related factors, is essential for developing effective noise reduction strategies. Through a combination of design optimization, advanced material, and active noise control technologies, engineers and workers to reduce the noise impact of the engines while maintaining the performance and efficiency. Ongoing research and more innovations while continue to improve the noise control method, contributing to better, more environmental friendly aerospace engineering and operations. So, thank you.